So today we are going to discuss detail about the second case, and this is about the adsorption with dissociation, because we have already discussed the two forms, modified forms of the Langmuir adsorption isotherm, and in detail in the previous lectures. And this is the second case, and this is about the adsorption with dissociation, and this is the final form of the adsorption with dissociation, and this is also the Langmuir adsorption isotherm. And here we will first derive this equation, and this is also very simple equation as we have done before, and then we will compare the outcome of the adsorption with dissociation and adsorption without dissociation. So how can we compare the both type of the adsorption by using the Langmuir adsorption isotherm? So let's move to the derivation. And here this is the another case, and this is the same equation we have used in the case one, which was about the adsorption without dissociation, and this is the equation with this dissociation. And here what is the difference? In the previous case there was only one molecule of the adsorbent, and with the adsorption complex only one molecule, or you can say one adsorption complex was formed, because one site was available to adsorb the one adsorbate. So that's why one adsorption complex was formed. So here the rate of adsorption is actually the proportional to the pressure of the gas, and of course the adsorbent, but the each atom of the available site which are available at the surface of the adsorbent is going to occupy two molecules of the, or you can say two sites will occupy one molecule of the gas, because this molecule is going to dissociate to form 2A. And here let's suppose if H2 is the molecule of the gas, and when H2 hydrogen gas is going to dissociate, and it will form two hydrogen atoms. And so this adsorbate is going to occupy two sites available on the adsorbent, and that's why two adsorption complex is formed. So this is the case with dissociation of the adsorbate. So actually this will remain the same, and because the adsorbent is going to provide the active sites, so these sites are filled with one molecules. How many sites are filled? Two sites will be going to fill with one molecule of the adsorbate, because this molecule of the adsorbate will be dissociated to form the two atoms, and then this will occupy two sites of the adsorbent, and that's why this is called the adsorption with dissociation. And in the previous case there was no dissociation, so one site was available to occupy only one molecule of the adsorbate. That's why in the previous case we studied the adsorption without dissociation. Now I'm going to derive the equation. This is the first step, and all these steps will remain the same. So you must understand actually we are not going to do much major things during the derivation. It will remain the same as we did in the first case, which was the adsorption without dissociation. So at time when zero, so there is only the pressure of the gas is available. That P is the pressure of the gas. This is the gas, and this is the solid. And how many here the molecules or the number of moles of the surface are present. These are two. That's why I put over two. And what is the possibility of the adsorption complex to form at time 0? That is the 0, because this is the starting point for the adsorption of the adsorbate on the adsorbent, so no adsorption complex is formed. So when at time t or at equilibrium, so what is happening, there are two, because two surfaces or two absorption complex are formed, so there are, so the theta will be 2 theta, and how many of the active sides of the adsorbent are left, that will be 2 minus 2 theta. This is the same as we did in the first case, but only difference is here in the previous case we used the theta only, and here the one of the molecule of the surface, or you can say the adsorbent. So here, because there is the dissociation, two molecules, sorry, two sides are going to occupy the one molecule. That's why it is written over here two. So in another case, you can may also write, you can take a 2 as a common, and what is left 1 minus theta, and this is the 2 theta. So this is the same case as we discussed in the first case. So theta is the fraction of the total surface covered by the adsorbed molecules, and in detail we have also discussed before what fraction adsorbed, that is the number of adsorbed molecule of the adsorbate per maximum available sites, and available sites are the adsorbent. So total fraction where the, or you can say maximum fraction will remain the one, when let's suppose all 100 sites are available and 100 sites are occupied with the adsorbate, so 100 divided by 100 will be equal to 1. So total fraction will remain, the maximum value will be 1. So 1 minus theta, again, these are the vacant sites, and P is the pressure of the gas. So this is the starting the derivation of the adsorption with dissociation. And this is the actually the rate of the reaction for the same equation. It is written over here, and this is minus dA2 over dt. So what is this? This is actually, I am expressing over here the change in concentration, or the change in number of moles or the sides with respect to the change in time, and that is called the rate of the reaction. So what is, because when the adsorption complex is going to form, there is the decrease in concentration of the A2, that's why it is written over here minus d change in concentration of A2 divided by dt. This is the rate of decrease, or rate of disappearance of A with respect to time, and similarly this is also going to be decreased with respect to time, because this is as a similar case we discuss in the rate of the reaction of any chemical reaction. And if you want to compare the rate of the both, because here two moles are required to occupy the one molecule of the adsorbate. So ratio is 1 is to 2. So that means this rate is double as compared to the rate of the A2 molecule. So if you want to equalize all these two rates, that means if you divide by 2 of this rate, or you even in other case you can multiply the two with the A2 molecule. This you can also equalize the two rate of the reaction, but it's a similar way it is written over here. Just divide the whatever the coefficient is mentioned over here, so just divide by 1, that the rate of this will be equal to this. So here you have a look, the rate is double, so by dividing the two, now the rate of disappearance of this will be equal to rate of disappearance of this. Again, two molecule of the adsorption complex are formed, so you want to equalize the rate of the A2 molecules. Again, you have to divide by 2, because this is a coefficient 2, just dividing the coefficient with 1, this will equalize the rate of the reaction. So this is written the rate of the reaction, or here in our case this is important over here because we are going to measure the adsorption complex, and this is written over here, but here am we are going to represent with the theta. That's why the concentration he or am is being replaced with the fraction of the total surface covered, and that is represented by the theta. So in a similar case with the adsorption without dissociation, rate of adsorption will be proportional to the pressure of the gas, and 1 minus theta, the number of sites available, and to the power 2 because there was the, as in the previous case, this was the equation. So rate of the adsorption will be proportional to this, and 1 minus theta because the coefficient is 2, it is going to be the power of 1 minus 2, and this is all about the rate of the adsorption. So if you want to remove the this proportionality sign, again right hand side will give you the constant, and here this constant is called the rate constant for adsorption. So this is the rate of the adsorption, and in a similar case the rate of the desorption will be proportional to the theta square. And how much would be the fraction here is that 2 theta more will be the 2 theta more will be the backward reaction or the rate of the desorption. So this is the rate of the desorption if you remove the proportionality sign, and then right hand side will be the constant, and this constant is called the rate constant for the desorption. So with the equilibrium, the both rate of adsorption and desorption will be equal to each other. So what was the rate of adsorption? This was 1 over 2 d theta over dt, and this is the rate of the desorption. So this is the same, and desorption actually is going to represented by the minus, which is indicating the rate is going to decrease with respect to time, and that's why this is indicated with the minus sign. And in other way, this is the rate for the desorption. So in the previous slide, we have derived the relationship between the adsorption, rate of adsorption will be equal to this factor, and rate of desorption is equal to this factor. So by rearrangement of the equation, just moving to kd over this side and p 1 minus theta square over to this side. So this equation becomes this. This is the just rearrangement of the equation, and after this one, this is the kd over ka over kd is the equilibrium or the adsorption constant. So I am just replacing the ratio between the ka over kd, that is here these are the rate constant for the adsorption, rate constant for the desorption, and the ratio will be equal to equilibrium constant, or we said this is the adsorption constant. So this is maybe in a simpler form, more clear form you can represent over here just by keeping the sorry, the line numerator and the denominator, they are more visible over here as compared to this one. So now by keeping the same steps, this we have derived, and now because here I want to get the value of the theta. So all these steps later on are just to get the value of the theta, that is the fraction of the total surface covered. And by rearranging this one, just I'm going to multiply with the k, p multiplied by k, just moving to the left hand side, this equation becomes this. And now taking the under root, you can take the under root on the both side, and what is happening, this is going to be under root with the square is going to cancel out, and this will remain the form which is coming out after cancelling the under root and the square. So again, rearranging this equation, now I'm going to 1 minus theta again to multiply with the kp under root, and this equation will become like this. And here we have already discussed, this is the k actually is the kd, ka divided by the kd, rate of adsorption divided by the desorption. And again, now I'm going to open this equation. So under root multiplied by 1 will remain kp under root, and kp under root is going to multiply minus theta, and this will be minus under root kp, and theta will be equal to theta. Now moving the theta, sorry, again, this is just the rearrangement of this equation. This is a minus kp under root theta. Moving to the right hand side, it will become positive. And then, you may take a theta as a common, and what is left, this will be 1 minus kp under root if you take a common theta out of this equation. Now theta will be equal to, this is the, again you want to divide by kp under root, and this equation will become this. So this is actually the final version of the equation we started, as we discussed at the start of this slide. So this is the dissociative adsorption, and this is the same equation. I'm just removing the under root and placing 1 over 2 over here. So this is the dissociative adsorption, and earlier we have discussed this is the non-dissociative adsorption. So non-dissociative absorption will be theta will be kp 1 plus kp, and this will be the, actually the pressure is going to change. Here the power of pressure is 1, and here the power of pressure is 1 by half. And what is the, actually the outcome between these two equations? So surface coverage, that is the theta, depends more weakly on pressure for the dissociative adsorption. Dissociative adsorption is this, than the non-dissociative absorption. That means, this, the pressure is very important here. K is the constant, and you can say the in the both equation k 1 plus k will remain the same. Only the difference is the pressure. So here the pressure is having power 1, and here pressure is having power half. That means half of the power as compared to the pressure in case of the non-dissociation dissociative adsorption. So if the power is half, that means this surface coverage, that is the theta, is more weakly depends on the pressure in case of the adsorption as compared to the non-dissociative adsorption. So this is the comparison between these two equation. Now what is the difference between these two graph? So again here, this is the dissociative adsorption, as it is mentioned with the theta. This is the non-dissociative adsorption. So what is, if the graph is plotted between the fraction of theta versus the pressure, again fractional coverage or the theta with respect to the pressure, and at different values of the k would be, maybe there are the three different k values, zero point 0.1, and here is the 1, and that is the 10. And in a similar way, the value of the k is 0.1, 1, and the 10. So all the conditions are the same. Now we are going to compare actually what is happening with the dissociative and the non-dissociative adsorption. And again, the equation as written over here, x is going to be converted into the 2. So one molecule of the adsorbate is going to occupy two sides of the adsorbent. So almost, so more, in this case dissociative adsorption is going to occupy the more sites available on the adsorbent as compared to the non-dissociative adsorption. That's why it is going to reach with the maximum value of 1, and here you can see there is no reaching to the maximum value of 1, because as explained earlier, because here more sites are going to be occupied by the adsorbate as compared to non-dissociative adsorption. So maximum site will be occupied in this case. That's why this graph is going to reach to the value maximum value of 1, and here in this case it is less than 1. So this is all about the today lecture. So we have actually derived the equation for the dissociative adsorption, drive the equation for the dissociative adsorption, and later on we compared the both equation, the dissociative adsorption with the non-dissociative adsorption. So the significance over here, so if the data is available, we can easily confirm which adsorption, Langmuir adsorption is going to be happen, or you can apply a modified form of the adsorption, Langmuir adsorption isotherm on to your relevant data which are you getting from the physical or the chemical adsorption. So if you have a further look on the equation, if there is a non-dissociative adsorption, so particularly this is for the physical adsorption. So if it is the dissociative adsorption, so particularly this is maybe reference to the chemical adsorption. So that's why at the start I one of you asked whether this is the for the chemical or the physical adsorption. So Langmuir adsorption is equally applicable to both of the physical and the chemical adsorption. So with this one, I am just